Hello, Dr. Olson here for Physics 1053, College Physics 1. Um, we have been talking about work and energy here in Chapter 6 of our textbook, and now we're ready to introduce a very important concept that will make our lives so much easier. This concept is called the conservation of energy. So we'll start off talking about this by describing the difference between conservative and non-conservative forces. We'll define mechanical energy and how it is conserved. Then we'll look at how to actually solve a problem using conservation of energy. Um, Not highlighted in this video, but it is included in your textbook, and I highly recommend looking at it. It's the section on other forms of energy and energy transformations. Basically, the idea is that energy cannot be created or destroyed. It is only converted from one form of energy to another. And that section discusses that. And then one of the last things we'll also talk about is what happens if you have dissipative forces. How do you solve problems with dissipative forces? Okay, so we've discussed work, and we know that work is force times distance. In other words, it's the product of a force applied to an object with the distance that the object moves. Now, sometimes the force that's doing the work is actually going to depend on the path that the object takes. Sometimes it does, sometimes it doesn't. An example where the path does not matter would be gravity. You can imagine you have a book that you start at point y1. Then you move to point y2. It doesn't matter if you just drop it and it goes straight down, or if you throw it across the room and it comes back to that point y2. It doesn't matter what direction or path it takes to go from y1 to y2. The path does not matter. Gravity will always point down. So such a force where the path is irrelevant to the direction of force is called a conservative force. Now here's an example of where the path of motion does matter. That would be with friction. Consider in this figure, you have a box moving from point 1 on the left to point 2 on the right. We could go straight from left to right, in which case friction will always point to the left. But if you take a curved path, then friction is going to point back along that path. You can see in the diagram that the direction of friction changes because friction always opposes motion no matter where you go. So the direction of friction changes based on your path. When this happens, this is called a non-conservative force. So with gravity, we saw we don't care what path we take. Gravity is always pointing the same direction, so it's a conservative force. But friction does depend on the direction of motion, so it is a non-conservative force. Here's a table showing a few examples of conservative and non-conservative forces. Gravitational, elastic, and electric forces are all conservative. Elastic being something such as a spring. Some examples of non-conservative forces, we already talked about one, friction and air resistance, which is very similar to it. There's also tension and combustion from a rocket, so the rocket propulsion or a motor, and just applied forces, pushing or pulling on an object. Now, when we talk about potential energy happens only from conservative forces. There will never be potential energy due to friction or air resistance, and that has to do with the non-conservative nature of those forces. So you can have gravitational potential energy, you can have elastic potential energy, or electric potential energy, but never any of the others in the non-conservative forces column. So now let's take a look at work done by conservative forces and compare that to work done by non-conservative forces. Simply put, the work, if we add the two works by conservative and non-conservative forces together, That will give us the total work done on an object. But we saw earlier that the net work is also equal to a change in kinetic energy. We also just discussed in the last slide that conservative work will only be done, potential energy is only a function of conservative forces. So the conservative work done would be the negative change in potential energy. This has to do with the idea that if a conservative force does work, then as the work's being done, you have a loss of potential energy. That's where the negative sign comes from. Non-conservative work, we'll leave that alone. But now, if we solve for the work done by non-conservative forces, that's going to be the total change in kinetic energy plus change in potential energy. And this is a very important equation. This is going to be the basis for our conservation of energy laws. Let's assume a nice ideal circumstance where there is no non-conservative force. So non-conservative work would equal 0. So our equation that we just showed in the last slide becomes that 0 is equal to the change of kinetic energy plus the change of potential energy. Now let's define mechanical energy to be the sum of kinetic and potential energies at some given point. So let's say that an object moves from point A to point B. Look at the kinetic energy at point A and the potential energy at point A. Add those two together. That will be your total mechanical energy at point A. So we take our change in kinetic energy plus change in potential energy. Since there's no non-conservative work, that equals 0. Now change in always means final minus initial, so we're going to take kinetic and potential at point 2 and subtract the kinetic and potential energies at point 1. If we rearrange our equation, we get that the kinetic plus potential energy at point 2 minus the kinetic plus potential energy at point 1 is equal to 0. Well, remember we defined kinetic plus potential energy to be mechanical energy. So the total energy at point 2 minus the total energy at point 1 equals 0. This result is known as the conservation of energy, one of the most important equations in basic physics. Basically what it means is that the total energy at point 1 has to equal the total energy at any other point in the whole process when there are no non-conservative forces. So here's a good example. Let's take a rock and lift it up to some height h, and we drop it to the ground. Before you drop it, we have a total energy of kinetic plus potential, which would be 1/2 mv squared plus mgh, or mgy in this case. Well, there is no kinetic energy, there's only potential energy. And so we have full energy is completely found in potential energy. As you drop it, half of the potential energy has now been converted to kinetic energy. That's halfway down. But if you add the potential and kinetic energies, you should get the exact same amount of energy as what you started with before you dropped it. Just as the rock is reaching the ground, your height is now 0, which means your potential energy is 0. There's no potential energy left. All of your energy has been converted to kinetic. And you have the same amount of kinetic energy at the floor as you had potential energy before you started. That's the beauty of the conservation of energy principle, is the total energy never changes. So let's take another example. Let's say you have a roller coaster. You start at some height y, and the roller coaster, ignoring all non-conservative forces, drops down the hill, and at the bottom of the hill, all of your potential is now kinetic. Then as the roller coaster goes up the other side, you're converting kinetic back to potential. You have in the end, all the kinetic will be converted to potential, but you have the same amount of energy at the end that you started with. And since potential energy is calculated as mgh, then your roller coaster should end at the exact same height at which it started. Okay. Here's another good example of conservation of energy. You have a pole vaulter who is running and so has kinetic energy, 1/2 mv squared. But putting the pole vault on the ground, it bends the pole, which gives it elastic potential energy. So as the pole vaulter leaves the ground, she'll have both kinetic and potential energy. But that total amount of energy had better equal the amount of energy she has as she goes over the vault. So she will now have kinetic energy as she moves over the bar, a little bit of spring potential energy as she reaches the top. What this equation does not show is now she has a height, h, so there should also be a gravitational potential energy, mgh, term in this equation. So your total kinetic plus your total potential will equal your total energy that you started with. Okay, now in a real world, unfortunately, we have to deal with non-conservative forces such as friction. If there is non-conservative force, like friction, then your total energy is actually going to decrease. A good example is you slide a book across a table, the book is going to slow down and stop. The kinetic energy just disappeared. Where did it go? Well, it was converted in the form of heat. And so the temperature should actually rise, the heat being related to temperature there. So our change in energy is no longer equal to 0. So that our conservation of energy equation that we had before doesn't work anymore. We have to reintroduce non-conservative work. So non-conservative work would be change in kinetic plus change in potential, which if we rearrange just as we saw before, that means just change in energy. So my change in energy is now equal to my non-conservative work. I can use these equations now to solve for conservation of energy, including the non-conservative work. So how do we solve problems with conservation of energy? Note that how much simpler this is now than all the kinematics and stuff that we did in chapters 2 and 3. First thing, we start off the same always. We draw a picture and we determine the system for which the energy will be conserved. We look at what it is that we're evaluating, what the focus of the problem is. 3, we identify all of our knowns, everything that we are given. We figure out what we're looking for, and we need to decide final and initial positions. In the roller coaster problem, where are we starting, where are we stopping? And I would also add in your picture at this point, when you identify your initial and final positions, it's helpful to identify what your kinetic and potential energies are at both of those points. Choose a logical reference frame. This is important for determining the kinetic and potential energies, especially the potential. And then just apply conservation of energy. Your total energy at your initial position has to equal your total energy at the final position. And then it's just algebra from there. Solve. Notice we don't have to deal with any vectors. We don't have to deal with x and y components. Makes it so much easier. Okay, so here in the video we talked about potential energy being associated with forces that depend on position. In other words, this was actually the previous video. In order to measure potential energy, you have to have some reference point. But in this video we did talk about how potential energy is only associated with conservative forces. And that's this final point here. And when it's only conservative forces that are acting, then we can say that mechanical energy is conserved. This concludes Chapter 6. Let me know if you have any questions.